let us quickly recap what we did yesterday. Yeah, so operations on sets, we saw what are binary unions. You understand the word binary? Yeah, union of two sets. Then binary intersections, binary Cartesian products. Then what were the elements of Cartesian products? They were ordered pairs. And we are going to use Kuratowski's definition for the ordered pairs. Yeah, this ordered pair xy is same as this two element set from which we can extract the first element as well as the last element. Then we also defined what is power set and different function types, yeah, injective, surjective and bijective, nothing that you don't know already, and the set of functions from A to B. We will use two different notations, fun AB and B to the power A. Now before I start writing anything new, so have you met illiterate people, those who cannot count? Yes, maybe somebody has some relatives or home in village. So illiterate shepherds do make sure that all their sheep comes back home in the evening. How do they do that? Even if they have, let's say, 100 sheep, how do they make sure that all the sheep is back?
They map it to something and count it.
Very good. They map it to what?
Let's say a stone, one sheep.
Okay, so they can map it to stones, or sometimes they have a gate. Yeah, the farm has a gate, and when the sheep are entering, they use their fingers. Yeah, so that there is one-to-one correspondence between fingers and the sheep while they enter. So this shows something. This shows that the idea of counting is not as fundamental as the idea of bijective correspondence. One-to-one correspondence is the key. Yeah, I mean, even people who don't know numbers formally, 1, 2, 3, 4, they can still use this idea of one-to-one correspondence to count. I mean, whatever is the actual meaning of count. Right, so this idea was emphasized by one of my professors in Manchester, and he's a really great mathematics educator, Sasha Borovic. If you ever want to read up on him, or he also has books on mathematics education. He gives really excellent talks only based on pictures. Yeah, there is no mathematics involved, but you will learn a lot of mathematics through such talks. Okay, so bijective correspondence is our key. Yeah, and we are going to use that idea today to define something. So once again I am going to recall something which we have already done. So recall von Neumann ordinals. Ordinals will be a special topic of study later on. Right now I just need, I can put them in brackets and just say natural numbers. Okay, where 0 is the empty set or the set consisting of nothing. Then 1 is the singleton 0 set. Right. So it is also 0 union singleton 0. 2 is defined to be 0, 1. It has precisely two elements if we know what cardinality is, and that is also equal to 1 union singleton 1. And take it forward, so n is defined to be n minus 1 union singleton n minus 1. Right? Understood this type of definition? We are just adding one element at a time. And what is 10? Well, 10 is all numbers from 0 to 9, all the numbers less than 10. Right? So therefore ultimately we define omega to be equal to n such that n is a natural number. So these are the natural numbers, yeah, 0, 1, 2 up to n and so on. Alright, so omega is just our notation for this order, and then you can observe that for natural numbers m less than m and n, we have, this is a very important property, m less than n if and only if m belongs to n. So belonging relationship has now become our strict ordering on natural numbers as well, right? So 0 is less than 2, so 0 belongs to 2, 1 is less than 2, so 1 belongs to 2, correct? So now we know this, and now we can define a finite set using this definition of von Neumann ordinals. A set A is finite if there exists, does anybody want to complete the definition?
There exists some natural number
There exists some natural number such that?
which is greater than
Very good. So there exists a natural number n for which there is a bijection maybe this A is confusing with our English language A, so I will write A. If there is a bijection between A and n. Okay, a set is finite if it is in bijection with a natural number. Well, this is precisely the definition you were aware of, correct? We just formalized it more axiomatically. Okay, so this is the definition of finite, and the set A is countable if do you want to complete this definition? If there exists a bijection between
some subset of omega and
right, if there exists an injective function from A to omega, right? So a countable set could be finite or infinite. So we are just saying it needs to be in bijection with either some natural number or the collection of natural numbers, right? So that's what we are writing. What is the meaning of countably infinite? So countably infinite, some people also call it denumerable. Yeah, I'm just going to put those terms here. If you read a book, then it might also be called denumerable. So instead of injection, they will use a bijection. Okay, if there exists a bijective function from A to omega, then it is a denumerable or countably infinite set. So now you are ready to solve that problem on pigeonhole principle from the tutorial, yeah, because you know what is a finite set. Okay, so now this is something about bijections. We will say more about bijection in the future also. Like, any problem about this? Any questions? Yeah, this is standard. Yeah, all of you know this. Now we'll ask a natural question. So this is our first theorem, Cantor's theorem. Actually there are many results in set theory which are called Cantor's theorem, and the proof is also very short for a theorem. So this is Cantor's theorem on power sets. So there does not exist a bijection between a set A and its power set P of A. So what can exist between A and power set of A? Injection. Okay, so at the bottom of the page I am just going to write down that injection. So give me an example of an injection from A to power set of A. X maps to singleton X. Very good. Okay, X maps to singleton X is a bijection. Is an injective function. I am not giving it a name. I can give it a name if you want. The name would be appropriately just singleton blank map. Right, so we definitely know there exists an injection from A to power set of A, but we want to know whether there exists an injection which is also a bijection, and Cantor claimed that there is none. Does anybody want to try and prove this statement? Any ideas? Just throw ideas at me. Yeah, we have to learn how to think. Power set is bigger, but in what sense? Cardinality, fine, but we haven't yet defined cardinality. That's the conclusion of this theorem. Yeah, not really the proof. We had to use contradiction, very good. So that's one method of proof. Yeah, proof by contradiction, yes.
If we map each element of A, then they will exhaust, but there will still be some elements remaining in the power set.
So if we take an injection,
Yeah, we map each and every element of A,
uh-huh,
element of the power set of A,
uh-huh.
but after some time the elements of A will exhaust. But
Correct. So the elements, if you take an injective function from A to PA, you are saying that after some time the elements of A will be exhausted, but the element of the power set will not be exhausted. I mean, as is the case with this particular injection, this particular injection. However, still that is not a proof. You have to show this for every possible injective function that it cannot be a surjection.
For a bijection,
Uh-huh.
the number of elements in set A and the power set A will have to be equal. But
For bijection they have to be equal. Yeah, there should be a number of same number of elements.
yes, but in set A and power set A, power set A will always have more elements than.
That's precisely what he said as well. Yeah, power set of A will always have more number of elements, but that is a consequence of this theorem. It's not a proof of the theorem yet. So there was one good idea from there, yeah, that we had to use contradiction. So by contradiction, what do we assume? That suppose there exists a bijection. So let us do that. So suppose F from A to PA is a bijection. Now we are going to use some idea similar to Russell's paradox yesterday. Okay, we are going to consider, so this definition is the most important thing. Let B be the set of all those A's in A such that A is not in F of A. You understand this? So f of A is going to be an element of the power set. So it means it's a subset of A. So either A can belong to f of A or A cannot belong to f of A. So we are just collecting all such elements. Yeah. Then we are collecting some elements of A. So then B is a subset of A. That you agree? B is a subset of A. So B is a subset of A, and hence B belongs to power set of A. So far so good. Now what should we do? It belongs to the power set. So it belongs to the codomain of the function.
The function is bijective.
The function is bijective. Since f is bijective, there exists a unique element, right? There exists a unique element B in A such that f of B is equal to capital B. Every element of power set of A must belong to the image of the function, right? So therefore there exists a unique element B because of bijection. We could have also assumed surjection, yeah, and we would have got some B. So such that f of B is equal to B. Now ask the question, does B belong to B?
Cannot belong to B, as A does not belong to f of A.
A doesn't belong to, yes. So if B belongs to B, then B has to satisfy this property, right? That B cannot belong to f of B. And if B doesn't belong to f of B, then by definition of capital B, it must belong to B. Same thing that we did yesterday, yeah, and this is a contradiction which proves that there cannot exist a surjective function. Okay, so I will just write it down. If B belongs to B, which is equal to f of B, then by definition of definition of capital B, B doesn't belong to f of B. This is a contradiction, and this is the symbol I am going to use for contradiction. Two trains crashing into each other. Yeah, and if B doesn't belong to B, then again by definition of B, B must belong to B, f of B. Again this is a contradiction. Therefore there cannot exist any bijection between f and p, not f and pf, between A and PA. And this is the end of the proof. Yeah, very simple proof. So this idea of defining B is important. So in common practice, this particular idea is called the technique of proof is called Cantor's diagonal argument. This technique is very frequently used in mathematics as well as in computer science. Now you can ask why diagonal? Yeah, so it's actually not about diagonal, but it's about the anti-diagonal. Yeah, so B, A and FA, yeah, if you plot a graph on x and y axis, then A and FA looks like the diagonal. So therefore we are, I mean, even though it says that A doesn't belong to FA, we are referring to no points being on the diagonal, so therefore it's called Cantor's diagonal argument. Any questions about this?
Why didn't we just state it for surjection?
We could say state it for surjection. If you want, I can just change that. Yeah, there doesn't exist. Like right now, I have written a bijection between a set and its power set, or equivalently, I can say that there doesn't exist a surjection power set of A to A. Oh, sorry, A to power set of A. I should use a pointed eraser now. And here I can make the change, since F is surjective and instead of there exists unique, I can just write there exists and prove the same result. Any other questions? Okay, so let's proceed. Let us use some notations, yeah, some more notations. So if F from A to B is injective, we use F from A arrow with a tail to B. If it is surjective, then we use F from A double arrow B, yeah, two head arrow B, and bijective both notations simultaneously. Okay, this is a common practice. So we don't have to say anything in words. Yeah, that's what notations help us for. Actually, do you know why mathematicians invent notations? Yeah? Huh? Different languages, yes. I mean, to make it language independent is one purpose, but the most important thing is they are laziest people. They don't want to write a lot. Yeah, they just want to make everything concise but precise. So therefore, notations help them a lot. Okay. So now that we have established the importance of bijections, yeah, so this is also like one of the philosophical themes which I want you to think about properly, that certain ideas in mathematics are more fundamental than their material realization in mathematics. Like the idea of one-to-one correspondence is more fundamental than the concept of counting. Yeah, the idea of relations is more fundamental. Yeah, all of you know relations on sets. Yeah, it's a relation like binary relation, equivalence relations. Those are also more fundamental than the concept of a set even. Right? So, what is an equivalence relation on a set? So let us be more formal. Yeah, an equivalence relation E on a set A is, I mean, you said three words, right? Reflexive, symmetric and transitive. But first I have to describe E as a set. So what is it? E is a subset of? Yeah, is a subset. Yes, E, subset of A cross A, satisfying Reflexivity, what does reflexivity mean? For all A in A, the pair A comma A is in E. Okay, what is symmetry?
For every A comma
A,
B.
B belongs to E, then B, A also belongs to E.
For, I can write this, for all A, B in E, B, A also belongs to E. And third thing, transitivity. Actually, this is not really the right way of writing things. I should do undo and erase this properly. I should say for all A and B in A, if AB belongs to E, then this implies that BA also belongs to E.
Double implication. Like there should be double implication.
Double implication is a consequence of single implication, right?
Yeah.
Right? We don't need to write double implication. For all ABC in A, if AB belongs to E and BC belongs to E, then that implies that AC belongs to E. Now the question here is, where exactly did we use the concept of a set? Yesterday we saw what is a class. Yeah, so classes are either sets or proper classes. We can also define an equivalence relation on a class, because we should be able to take pairs of elements from a class, and then we can do the same thing. I am going to give you one such example. Yeah. So any questions about this? All of you know equivalence relations? We will discuss equivalence relations in detail in the next week, most likely. But before that, let us say something more. So say that sets A and B are equinumerous if there exists a bijection between them. Okay. So equinumerous if there exists a bijection between them. This is another name for having the same cardinality. Like, yeah, so is this an equivalence relation? So equinumerosity is an equivalence relation. First we had to check reflexivity. Can you check that for me? If I am given set A, does there exist a bijection between A and A? What bijection? Identity, very good. Yeah, so 1 sub A, this is our notation for identity. A to A is a bijection. Okay, what about symmetry? Some people also call it symmetricity, but I feel like it's unnecessarily long. So what about symmetry? If there exists, so if F from A to B is a bijection, then
there exists.
yeah, what function? F inverse, correct. How is F inverse defined?
From B to A.
Right. Then F inverse from B to A is also a bijection. So therefore it is symmetric, the like existence of a bijection is symmetric, and transitivity if f from A to B and g from B to C are bijections, then what is the bijection from between A and C? F of g. No, we cannot do f of g. G of f. Yeah, make sure that domains and codomains are perfectly matched. Then G composed with F is a bijection from A to C. How is G composed with F defined? If I want to send an A, then where will I send it to? First f of A, yeah, that will be an element of B, and then I can apply G. Okay. So this is called composition of functions. So what we just showed is composition of two bijections is a bijection. In the tutorial sheet you are given a problem which says that show that composition of two injective functions is injective and composition of two surjective functions is also surjective. Right? So some special cases of this. So that together with those two exercises you will prove this. Okay? Now so what we have observed so far is that equinumerosity is an equivalence relation. However, we did not answer the question equivalence relation on what? We just said it's an equivalence relation. So what is our collection on which this is an equivalence relation? The set of all functions. No, what are the objects? I mean, what things are equivalent?
The class of all sets.
The class of all sets. The proper class of all sets. Yeah, even better. So this is an equivalence relation on the proper class of all sets. So once again, yeah, the philosophical idea of an equivalence relation, like which groups things together and partitions, this idea of partition is more fundamental than the notion of a set. It can be done with a set or a proper class. Yeah, so this is an equivalence relation on the proper class. So I hope all of you know that equivalence relation partitions a set. Yeah, similarly this equivalence relation will also partition this proper class, and those are called like equicardinality classes, right? So this equinumerosity is a proper class, is an equivalence relation. I will write here on the proper class of sets. All sets. Okay. If A and B are equinumerous, we write A equal to B. So if A is finite, what do we mean? That A is equivalent to, A is equinumerous with some natural number, right? So if A is finite, and A is in bijection with n for some n in omega, we say that the cardinality of A is n, and write cardinality of A is n. Yes, nothing surprising here. But we took a very long time to arrive at this particular notation, that size of A is equal to n. We are trying to be very careful and formal. Understood this part? If our set happens to be countable, then we don't say its cardinality is n. Okay, there are some different rules with infinite sets. We have to use some different notations. Those are called Aleph notations for infinite sets. So right now we won't do that. But equinumerosity is also the same as having the same cardinality. Okay, bijection means having the same cardinality.
Here when we are saying A is equinumerous with n, are we talking about the set n?
And yes, so now that's what my first point was in the first lecture. What is a number? You are thinking of n as a number, that's why asking this question. Correct? A is equivalent to equinumerous with n. Then n is not a number. A natural number, like a number is not different from a set. A natural number is a set. Yeah, it is that particular set. Yeah, there is no other notion of number. So actually it is also okay to call this bijective class, bijective equivalence class or equinumerosity class of a set to be its cardinality, but then the classes will become proper classes. Such equinumerosity classes will become proper classes. For example, yeah, I mean, let us take some take a moment to understand the size of all singletons. How many singletons are there? Infinitely many. Yes, infinite is, but let's be more specific. Yeah, we are learning the language of sets and classes and proper classes. So how many singletons are there? Are there set many singletons or proper class many singletons? Proper class many, but justify your answer. Why there are proper class many singletons? Okay, let me write this. So, how many singletons are there? How many is a vague question, yeah? How many singletons exist? So, for each set A, this is a singleton. So, therefore, there are at least as many singletons as there are sets. So, therefore, the answer is, yeah, I mean, you feed it back to a proper class many. So, therefore, if we say that equinumerosity class of a set is its cardinality, yeah, that's actually too big. We don't want to deal with proper classes. So, therefore, eventually when we will study ordinals and cardinals, we will have to figure out another way of dealing with this problem. Yeah, so that's why beyond finite sets right now I am not using the word cardinality. For finite sets we have defined what is cardinality, but for infinite sets we haven't. Okay. Any questions so far? Okay, good. So, I think there are a couple of things which you will need for your for solving the tutorial sheet, which we will discuss tomorrow. So, if f is a function A prime is a subset of A and B prime is a subset of B, then what is f of A prime? What is f of A prime? Tell me. Come on, all of you know this.
Like this, for every x belongs to A, so mark n.
For every x belonging to
A prime.
A prime,
This the element which maps to it, that
I mean that is f of a. Yeah, so I am just going to write f of a, the collection of all f of a's such that a belongs to a prime. Very good. So this is not this, undo. Yeah, so this is called the direct image of f. So this is direct image of a prime under f. Okay. Similarly, we can also define what is f inverse of b prime. What is it? F inverse of b prime? All such a's such that a belongs to a and f of a belongs to b prime. Very good. So this is called the inverse image of b prime under f.
So shouldn't A belongs to A prime?
No. I mean in the first one yes, here, but not here. Because when we are defining f inverse of b prime, then we are not using a prime at all. Yeah, these are two independent statements. Correct? The direct image of a prime and inverse image of b prime, these are two independent statements. Yeah, pictorially what is happening? Yeah, we have two different sets, a and b. We are choosing some a prime and then we are looking at its image. Yeah, maybe the function is not surjective, so this is f of a prime, and maybe we'll have some b prime over here and we are looking at its inverse image, yeah, this particular thing maps to this particular thing. Yeah, this is f inverse of b prime. Now, even though these things are very simple, direct image and inverse image, their interaction, their interplay with our basic operations, intersection, union and Cartesian products, yeah, that's a really crucial thing to understand properly, right? So that's what your tomorrow's exercise sheet is all about, that you should understand direct images and inverse images with respect to all these three operations: union, intersection and Cartesian product. It is very important. Yeah, I mean even when you are teaching a very advanced proof in some subject, at that time also you are using these simple things, and if you make a mistake there, your entire proof is wrong. These things look very simple, but they are very crucial also. Okay, so please pay attention to tomorrow's example sheet very carefully. Okay, there is one more thing, we still have got few minutes left. There is one more thing which I should do, and that is the concept of this. So let A be a set, then say that X belongs to union of A. Yeah, this is a big union. Union of A if there exists a Y in A such that X belongs to Y. So let me give you an example. So for example, let B be the thing consisting of 0 and 1 and 2. Yeah, these are sets. 0, 1 and 2 are sets. So what will be the union of B? This is perhaps a notation that you haven't seen before. 0, 1, 2. Yeah. So there is some philosophy behind this notation, that there is no distinction between elements and sets. Correct? So therefore, when you start with a set is itself a family of sets. So the elements of this set are themselves sets, so you can take union of all of them. So there is a particular axiom in ZF set theory, Zermelo-Fraenkel axiom, which says, which is called the axiom of union. So it allows you to take unions of such things. Yeah, so this definition is possible because of, so the definition of union of A comes from the union axiom of ZF set theory. So this is crucial again for understanding purposes, that there is no distinction between sets and elements. In like in schools, we are used to saying this, yeah, the class of all, the set of all students in this class. But you cannot really take the union of the set of all students in the class, can you? Because the students themselves are not sets in a precise mathematical sense. However, in Zermelo-Fraenkel set theory, that is not the case. Every element is itself a set, so when you write, even if there are infinitely many elements, you can still take their union. Yeah, the definition is clear. X belongs to the union if and only if it belongs to one of the elements. And that definition doesn't really require anything different. Okay, so any questions about anything we covered today?
The union of omega will be omega.
Union of omega, yes, union of omega will be omega. What will be union of a natural number? I'll just go to that particular slide. Is it this? No. No. Yeah. Okay, so what is union of 2?
0, 1.
Union of 2 will be? No, it will be 0 union 1.
Oh yeah, so it's 2.
No, 0 union 1. 0 is the empty set and 1 is the singleton empty set. So 0 union 1 will be 1. Union of 3 will be? 0 union 1 union 2 will be 2. Yeah, so union of n is n minus 1. Yeah, so the union operation actually decreases the set. Union of 0 will be 0. Yeah, union of 1 will also be 0. Yeah, and those who are interested in knowing something more, yeah, so that's also interesting, that why should we stop this definition at this point? Just for n is equal to n minus 1 union singleton n minus 1, you can continue. Then you can also define omega plus 1. Omega plus 1 will be omega union singleton omega. Omega plus 2 will be omega plus 1 union singleton omega plus 1, and this process never stops actually. Yeah. So that's how you get all of the von Neumann ordinals. Yeah, and there will be a proper class of von Neumann ordinals, and we'll select some of them and we'll call them cardinal numbers. And if that cardinal number means a particular ordinal is in bijection, it is equinumerous with your set, then this particular cardinal number will be called its cardinality. Understood? Yeah, so there is still some way to go before we can define cardinality.